on a number of subjects. We've talked about leakage. We're now going to talk about service life and how long things are going to last. And we're going to also talk a little bit about the environment in which it must function, albeit both quite limited because even though I've got an hour and a quarter or thereabouts, these are big topics. I'm going to touch upon 4 different topics: GCLs, SEAMs, BGMs, and HDPE, LDPE. Starting with GCLs, and this follows directly from a question that was asked at the end of my last presentation. How long will a GCL last? Well, it depends on what you mean by how long it's going to last. There are 2 basic components, the geotextile and the bentonite. The bentonite is a natural material. As long as, by last you mean as long as you pick a realistic hydraulic conductivity and you don't have erosion, it will last indefinitely. The geotextile, on the other hand, has probably got around 50 years plus or minus as a service life. And so we need to design recognizing the limitations and what is going to affect how long the bentonite is going to maintain a particular hydraulic conductivity. And one of the places that we can go to get insights into this is into the field. We have a full-scale field test site at Queen's. And I mentioned about hydration and how it affects performance. And ultimately this comes down to what is a realistic hydraulic conductivity that you can anticipate having in the very long term. And that depends, as I've already mentioned, on what is the GCL itself, but it also depends on its history. And so here are 2 examples of GCLs. The first one, GCL2, had an initial water content off the roll of 6%. And in the field, after 6 weeks, it had hydrated to 88% gravimetric water content. After 42 weeks, it was 109. And this is fully saturated at 125. So it was hydrating very nicely. And then at 54 weeks, it's at 47. So what is going on here? Well, if you look at the bottom of the screen, you can see it was installed in December 2006. And it reached its peak early in July 2007. And then it dropped between July and September. And what happens between July and September? We have summer. And this was in a composite liner that's exposed. And so it's going through heating, evaporation, and so it's losing moisture content. This is the sort of thing you need to think about when you're designing. What's it going to go through before it actually goes into practice? And it's going to go through some wet-dry cycles. So this is what it looks like at 47%. It still looks pretty good. It's just starting to crack. But it's got a very nice structure because it's been well hydrated in its history. Now let's look at a second product. If this will work for me, there we go. And it started at 24, it went to 59, 68, and down to 36. It has a coarse-grained bentonite instead of a fine-grained bentonite. And the rate at which that hydrates depends on the nature of the bentonite. And this never got very hydrated. And you can see that it's still got the coarse particles. They've never formed a gel. Now, if you start to hydrate, you then put it in a landfill or a mining situation and permeate it with a fluid, there'll be orders of magnitude difference in the hydraulic conductivity of those 2 GCLs because of their starting position and their history. Just look at the other one. Compare the 2. Now, as I said, GCL2 is just starting to desiccate, but when it was tested with a permeant that simulated landfill leachate, it still had very good hydraulic conductivity. So the history of what it goes through affects what its long-term performance is. Now, let us go a step further. This is, I think the battery might be wearing out on this. We can get a wide range in hydraulic conductivity depending on the method of manufacture, the type of bentonite, the stress, the cation exchange, that's the chemical interaction with the soil that is around it, the water content before it comes into contact with the permeate. Generally speaking, a GCL that's reasonably well hydrated will perform a lot better for the same permeate as one that was not. Okay? Fluid compatibility with that chemical it's got to contain, the hydraulic gradient. Now, traditionally we say that a soil has a hydraulic conductivity which is independent of gradient. That's not true when we get to GCLs that have been through a painful history, and gradient becomes important. Exposure to the liner before the cover soil is placed becomes important. So I just tried to show. So if we look at the spec sheet for a GCL, they're all pretty much the same. They say the hydraulic conductivity is less than 5 times 10 to the minus 11 meters per second. And there's a little asterisk there that references it to a code. I'm, of course, dealing with the ASTM code. And when you look at how that's obtained, it's for de-aired tap water at 35 kPa and under a head of 1.4 meters. That hydraulic conductivity applies to that condition and that condition only. You cannot use that as a design value. You need to think about what is the stress and what is the hydrating conditions and what is the permeate that my GCL is going to be subjected to, and select a hydraulic conductivity that's relevant. So there are a number of publications that have shown that over time, particularly in covers, GCLs experience a decrease in swelling capacity, an increase in hydraulic conductivity, in some cases by 5 orders of magnitude, and in others, no significant change at all. High hydraulic conductivity associated with low moisture content. So if you don't get a good hydration to start with, it's like a poor early childhood education. The better the child is educated and looked after in their formative years, the better chances they are in the future. The same applies to GCLs. The effect depends on the local conditions, in particular the chemistry of the soil. Now, let's look at the effect of both stress and permeate. So we're going to take a GCL here. We're going to hydrate it with clean water. And we're going to do it at 3 kilopascals and at 115 kilopascals. 3 is a simulation of the bottom of a pond with, say, 0.5 meter of cover soil, or it's a pretty good approximation for below a wrinkle in a composite liner. 115 is a quite low effective stress for many applications. And you can see the thickness changes by a factor of 2. Go from 3 to 115 because it consolidates. The hydraulic conductivity to water under 3 is still not bad, 6 times 10 to the minus 11, just of the spec sheet, which is at 35 kilopascals. But when I permeate it with leachate, it goes up an order of magnitude to about 6 times 10 to the minus 10. You'll see peel strength is indicated there. The minimal bundles gave what is normally expected to be a reasonable, adequate peel strength of 660. As you increase the needling, you see the peel strength goes up. Most people would say that's great. Maybe we're into another Goldilocks problem. you can see that GCl2 has the highest, even though it's got the same bundles as GCl3. What's the difference there? GCl2 is thermally treated, GCl3 is not. GCl4 has the highest amount of bundling, but an intermediate peel strength. So let's look at these samples, what they look like when they're exhumed. There is GCl2 with the fine-grained bentonite, and you can see it's got a nice structure. It's had a good history. It's had a good life so far, and it's going to go on, perhaps having a good life. This is GCl3. They had the same bundling, but look at the difference in the structure. What's the difference between them? The geotextiles, which is important, and the bentonite particle size, which is important. Now, let's look at hydraulic conductivity, and you can see I've put 7 centimeters of head on it. Very low head, a small gradient, and you can see the first 3 are coming in around 1 to 3 times 10 to the minus 10, and number 4 is already about an order of magnitude higher than number 1. They're all bentonite. They've been exposed to exactly the same conditions. And already we see an order of magnitude difference in performance because of the initial conditions of the GCl. Now increase that to 21 centimeters. Still not a massive gradient. And we've got 2 times 10 to the minus 10 through to 1 times 10 to the minus 7. So 3 orders of magnitude difference in hydraulic conductivity. This is telling us that the history of those specimens combined with what they started like has a significant effect on their long-term hydraulic conductivity. So these last 2, coarse granular bentonite, first 2, fine granular bentonite. These 2 have essentially identical needle punching, but when you get to 21 centimeters, you've got a substantial difference in hydraulic conductivity. And why is that? Why are we getting such high values? It's not because it's going through the bentonite, it's because it's going through the fiber bundles. Now, if you have a bentonite that swells, it seals up those bundles. But it's lost a lot of its swelling capacity. It's got low stress, it's in a cover, 1 meter of soil above it. And you can see the dye that was put into the fluid is not going through the bentonite, it's going through the bundles. The more you've got, the more that goes through. Now, let's throw a powdered bentonite into the mix. So here's we got the coarse one that we looked at before, 1 times 10 to the minus 7, fine at 2 times 10 to the minus 10, and 2 GCLs with powdered bentonite, 5 times 10 to the minus 11, 2 times 10 to the minus 11. You can see that there is a difference in performance because of the history and the nature of the GCl. So needle punch bundles do matter in real life. You need adequate peel strength, but you don't need too much. Large bundles and bundles area give a high hydraulic conductivity when there is cation exchange and low stress. And it's more problematic the coarser the bentonite. So let's suppose that I am designing, as indeed I was recently, well, 2 or 3 years ago now, a GCl liner system for a large dam. And I'm going to have it sitting on a till layer. I've got zone 1, 2A there. I've got a filter soil above my GCl. And it's meant to contain potable water. But it's going to be 2 years between when I place that GCl and when the dam is filled. What do I have to think about? I have to think about the fact that if I put a GCL directly on that till, moraine you would call it here, I think, which is at a moisture content of about 10, 12%, the GCL is going to suck up water from it. It's going to hydrate. Now, why do I care about that? Because it's going to suck up calcium and magnesium. It's going to experience cation exchange. And why do I care about cation exchange? Because this is in northern British Columbia, and it's going to be subjected to freeze-thaw and wet-dry cycles between the time I install it and the time it goes into practice. So what don't I want it to do? I don't want it to go through those freeze-thaw cycles when it's had cation exchange. So how do I prevent that? I use a coating. I take a GCL with a coating, and I put the coating on top of the till layer. And then I've got sand on top of that, and then there's some rock ballast. And is it going to hydrate? Yes, because it's going to rain, it's going to snow, the snow's going to melt. It's going to get plenty of hydration with clean water. It's going to go through freeze-thaw. No worries, because it can self-heal. Because I've stopped cation exchange. Now, the dam is now full. It's not going to go through any more freeze-thaw cycles. It's not going to go any wet, more dry cycles. That coating could disappear, and it's no problem to me. Now, it's not going to disappear. It might take 50 years. But I don't need it anymore. It's there for one purpose, to see me through that period of 2 years between when it was placed and when it has to go into service. The second one is another situation where I've got a composite liner. I've got a geomembrane, GCL, and a coating, and doing exactly the same thing. If it's going to get hydrated, it'll be through holes in this primary geomembrane, and that's what it's there for. So, take-home message here, GCLs with scrim-reinforced carrier and either a thermally treated or coating perform much better because they give better confinement of the bentonite at low stresses. Powdered or fine-grained bentonite is much better than coarse bentonite in situations where you're not going to be fully hydrated. And placing a GCL in contact with a soil with sufficient moisture and low ionic strength to allow it to adequately hydrate before it becomes in contact with a nasty fluid will aid its long-term performance. Minimizing exposure to wet, dry, or freeze-thaw cycles is important. You can see what I was doing when I couldn't do that. I put in another mitigating measure. Another way of doing it is having more cover soil, because you don't want that GCL being subjected to wet, dry, or freeze-thaw as well as cation exchange. One or the other is not a problem. Together, they're a serious problem. Avoid reliance on the geotextile long-term, because it's not going to last forever. The bentonite, if you choose your K value, will keep it, if it's appropriate value, indefinitely. And so, why do I have that till layer below my GCL? Not for its hydraulic conductivity, but because it acts as a filter. If the geotextile goes, I'm not going to get erosion of my bentonite under 40 metres ahead, which is what I've got at that dam. With negligible wet, dry and freeze-thaw cycles, after initial hydration, so if you do the first 5 things I mentioned, at low stress, your hydraulic conductivity needs to be considered in its particular context, but more often than not, it's going to be between 1 and 5 times 10 to the minus 10. Based on over 30 years experience of doing this, that's where typically it sits at low stress. At higher stresses, it's typically in the 10 to the minus 11 to 5 times 10 to the minus 11 range. So those values have been sustained for long periods of time and can be expected to be if you take appropriate care. So an increase in K due to leachate interaction or interaction with the soil is not a bad thing, as long as you consider it appropriately in design. It's life. The design assumptions must consider reasonable field conditions. So what's it going to go through between when it's installed and when it's actually in play? And design all involves assumptions. If you want good long-term performance, you need to ensure that construction is in accordance with your design assumptions. Good design, poor construction, poor outcome. Good design, good construction, good outcome. So that takes me from GCLs to geomembranes. And we have to consider here the chemical composition again of the fluid. Whether it's a GCL, whether it's a geomembrane, we're always concerned about compatibility of the chemicals in the fluid with the liner. We're concerned about temperature. If I'm dealing with a heap leach pad that's got exothermic reactions, I could be at 60, 80 degrees Celsius. That's going to give me a very different service life than if I'm at 20 or 5 degrees Celsius. What is the weakest point in a liner? Its seams. So I have to think about my seams. Now, the geomembrane used is a function of the manufacture and the design. These other factors are a function of design, construction, and operation. We have to consider the exposure conditions, and we have to minimize sustained tensile strains, no matter what the geomembrane. No liner likes strain or stress when it's tensile. So let's look a bit at welds. Here's a dual wedge weld, and we see it has a number of components. It's got two welds, that's why it's called dual wedge, and between them an air channel, which is used for testing the welds, a non-destructive testing. Oops, didn't mean to go there. We've got zones here right adjacent to the weld that are affected by the heating, but the same thickness as the sheet. As you squeeze this material, you squeeze out material. It's called squeeze out. They all play a role in the performance of that weld. Now, in North America, we're very good at ensuring that we have a strong weld. We're not very good at checking it's got a good service life. And those are two very different things. How you weld it to get it strong weld and how you weld it to get a good long life are different considerations. The Germans recognized this 30 years ago, but the rest of the world didn't pay much attention. When I say welds are the weak link, let's take a weld and let's age it in parallel with the sheet and see what happens. And the ratio of the time to nominal failure of the sheet divided by that of the weld is shown here in a brine solution and a municipal solid waste solution. Or put another way, the life of the weld is, in this case, 67% of that of the sheet, in this case, 45% of that of the sheet, because you do some damage in doing that weld. Now, can you do less damage? The answer is yes. So what do we need if we want good welds? We want low squeeze out. We want an acceptable thickness reduction. This is in the German DVS standard from decades ago. But the German's standard is applicable only to German materials and German construction practice. It's not necessarily applicable anywhere else. But you can do the same thing. You need to make sure that the welding temperature, speed, and pressure are appropriate so you don't lose antioxidants, you don't overheat the material adjacent to the weld, because doing those two things increases its crystallinity and lowers its stress crack resistance, which means it will fail sooner. Also, if you apply too much pressure, you get something that looks like this. It looks like a mess. It is a mess. It passes all the strength tests and it will fail very quickly. Other things that damage are scratches, indentations, and the result is low stress crack resistance and premature failure. So fusion welds are far more complicated than they're generally considered. Adequate peel and shear is not enough. We need to consider the overall combination of temperature, pressure, and speed. And that means trial welds before you go into production. So welds are important, but we can improve and do good quality welds. We need to remember that we've got to use the right resin, the right antioxidant package, appropriate thickness reduction, welding equipment that keeps track of what's going on, and we've got to pay attention to the sheet and ambient temperatures. And that means there's a sweet combination of parameters needed for welding. I don't know about it in Finland, but I know in Canada and the US, the main thing the welder wants to do is get finished. They'll weld as fast as possible if you let them. And they'll get the required strength, but you won't get the required performance. Oops. So I've highlighted welds with HDPE as being something to pay attention to. Now let's look to BGMs. They're sold partly on the basis that they're easy to weld. You send big Bubba into the field with a torch and a foot, and you've got a weld. None of this fancy equipment. How can it be simpler? Well, it turns out it's not quite as good as it sounds. These welds are having problems both at high and low temperatures, even in the sheet itself, but also in the seams. The problems have been highlighted. But I particularly want to talk about seams. So here's a test we did. We welded a sheet and then we subjected it to a sustained stress. Now, after the sheet was welded, we painted horizontal white lines on it. And you can see that those lines are no longer horizontal. Now they've actually separated, and you can see it's starting to delaminate at that location. And it's totally failed. Bitumen to bitumen is not a good combination. It's like taking two pieces of toast and welding them with honey and then subjecting them to tension. So if I take two bits of toast, weld them together with honey and pull on them, what do I think is going to happen? It's going to creep to failure. That's exactly what goes on here. There's nothing sophisticated about it. Now, let's take tests like that and document them. So here we're plotting the constant tensile load that was applied versus the time to rupture. Data is shown for two different people doing the work and two different geomembranes. And you can see there's a pretty clear relationship. As the stress goes up, the time to failure goes down. Now I'm going to pick 30% of the strength. Why do I do that? Because when we do a stress crack on HDPE, we do it at 30% of the yield strength. So when we talk about what's the stress crack resistance, it's at 30% of the yield strength for HDPE. So let's talk about what is the failure time at 30% of the strength of this particular material, and it's about 0.1 of a day. Not a lot of time. Now, in comparison, if I take a HDPE weld it'll take 1 to 3,000 hours at 50 degrees Celsius before it fails at 30% of the yield stress, compared to less than 3 hours at 22 degrees for the BGM. Neither of them like stress, let's face it, but that BGM hates it even more than the HDPE. If we drop to 10%, we're looking at 128 hours. And what is the strain at rupture? Well, you can see that at 30%, it was about, let's say, 18% strain. At 10%, it was about 6% strain. HDPE, we test for stress cracking at 6% strain. Now let's put a weld over an indentation that you would get in the field and see how it performs. So we're applying a pressure here of 20 kilopascals, so it's a cover application where there's some differential settlement. And after 24 days, the seam fails, and the leakage goes from 0 to 200 litres per day per metre of weld. And that's under a water pressure of 1.2 metres a head, 12 kilopascals. If I take it and I load it to 30 kPa and then up to 50 kPa, it fails in 0.04 days at 50 kPa and 1.9 metres a head. And the leakage is 500 litres per day per metre. So let's look at the numbers. HDPE, 2 millimetres thick, BGM, 4.8 millimetres thick. BGM is certainly a lot thicker. The roll, the HDPE is 8 metres, BGM is 5. The length of the roll, 105 and 64. What does that all mean? More welds. So in 1 hectare, we have 1,500 metres of weld in the HDPE, and 2,300 metres, or 50% more, for the BGM. So 50% more susceptible to failure. And the time to rupture at 30% yield for HDPE is 125 days compared to 0.1 day. The leakage. HDPE under 300 kilopascals of load leaked 0.2 litres per day per metre of weld per metre of head. The BGM at 20 kilopascals leaked 330 litres per day per metre seam per metre of head. A 1,600-fold difference. And let's suppose 1% of the seam failed. For HDPE, the leakage would be 17 litres per hectare per day. For the BGM, it would be 95,000. For 15 metres of seam failure, it's 17 for HDPE and 62,000 for the BGM. Ratios of 5,500 and 3,600. So, caveat emptor. HDPE seams will fail in 40 to 125 days at 50 degrees C in a surfactant. And we want them at less than 6% strain. BGMs fail in 0.1 of a day at 22 degrees in air. And the problem gets worse in very hot and very cold condense. Now, what about the time to nominal failure of the sheet? I'm going to talk about HDPE in a moment, but you can see here that my colleague Fadi Abdullah and his student have done tests on BGMs, 2 different BGMs, in solutions, mine solutions, pH of 0.5 to 11.5. And over on the right hand, we see in municipal solid waste leachate. And let's just look at It's got a nominal failure time of 45 years for solution 2, which is highly acidic, 0.5, 28 years in water. So it actually prefers the acid. 25 years at pH 9.5 and 20 years at 11.5. In air, it's 30 years. In municipal solid waste leachate, one ECL is 18 years and the other is 14 years. So how does that compare with HDPE? Well, here I'm comparing it at 9.5 and 11.5. Everything else is similar, and at 30 degrees, 25 years compared to 220 years. 20 years compared to 220 years. Not quite the same. So, BGMs are easier to seal. It's certainly easy to get a seal that meets the strength requirements in the short term. And they don't wrinkle. Those are true statements. But it's not the whole story. Ask what are the failure modes of all materials you look at, not just BGMs and HDPE. Whatever it is, look at the failure mode and mitigate it. BGMs have poor seams and poor compatibility compared to HDPE. So design on facts. Engineering is reliable, luck is fickle. So I'm going to finish off with the long-term performance of HDPE and LLDPE. So I've already mentioned it's important to consider chemical compatibility, temperature. We've discussed seams already. Are a very different creature to buried geomembranes and sustained tensile strains. So let's talk about what's in an HDPE, and it's got a resin. Most of it is resin. And resin's most important characteristic is to resist stress crack resistance. It's also got carbon black, which is there for UV protection, and chemical additives, which we assess in terms of two tests. One is the standard OIT, and the other is HPOIT. Standard OIT is relevant to most situations. HPOIT is mostly relevant to exposed geomembranes, in my experience. Now, one of the troubles is that life is full of trade-offs. We put carbon black in to protect against UV. That's important. But it also deactivates some of our antioxidants. And how much it does depends on the nature of the carbon black. Ironically, the better it is for UV, the more likely it is to actually deactivate some of your antioxidants. So I talked before about antagonistic effects. There is antagonistic effects here. And here are just a few of the many resins available on the market, all credible resins. Which one has your geomembrane got? Which one do you want? Then added to that resin is what's called a master batch. And it is a carrier resin, usually either MDPE or LLDPE, with a set of chemicals in it that are the antioxidants and stabilizers. And the additives that we add include carbon black, titanium dioxide if we want a white skin, a processing stabilizer, thermal stabilizer, UV radiation stabilizer, an acid neutralizer. Those that with an acid neutralizer and a little excess tend to do very well in low pH environments. And polymer processing aid. All of those are important. All of them have either antagonistic or supporting roles. So let's look at hindered phenols. There's a group of them called ergonox. And we're going to look at how we get OIT. We take a specimen, we heat it, and we heat it in a nitrogen environment. Then we introduce oxygen. And the OIT is how many minutes it takes before the polymer starts to degrade. The antioxidants are protecting the polymer, and then they're gone, or they're deactivated. And suddenly, the polymer starts to degrade. That's an exothermic relationship, and so we see the heat go up. And you can see as we increase the ergonox 1010 from 1,000 parts per million to 5,000 parts per million, we increase the time it takes. So if 5,000, we're at about 160 minutes of OIT. Okay, that's nice. But I just picked one example from a manufacturer who's got a lot of choice for you. Which one of his products do you want to buy? You've got 1076, low functionality, low hydrolysis resistance, and cheaper. You've got 1010, which is better functionality, so low hydrolysis resistance, or 1330, which is much better in terms of hydrolysis resistance, that is loss to water, and reasonable functionality. And guess what? They're not all the same price. So we've got the hindered phenols. Then we've got the phosphates. And there's a range of them, and they're the primary antioxidants. And let's suppose I have a standard OIT. Each of them can be contributing. Now, what I don't know when I do the test is what's contributing what. It could be 60, 100 for a value of 160. Or it could be anything, couldn't it? 160. They are not going to be the same. 160 is the same, but those ratios are important because there's a synergistic effect. Then I've got the thiosynergists, and they work together with the phosphates. And then I've got the hindered amines. And all of them are contributing to OIT values. But I don't know what's contributing what. That's the HPOIT. So a higher value tells us more of something, but it doesn't tell you about what. And the what matters. And when you look at it in a Brigger matrix, this is the various antioxidant groups, stabilizer groups, and carbon blacks. And you can see that it wasn't hard to get 150 different variants. Now, what happens when we age the geomembrane? Firstly, those antioxidants are there to protect it. We have antioxidants in our diet. Vitamin E is an antioxidant that helps protect our DNA. So the antioxidants are depleted. HPOIT is depleted here to a relatively high value. So it looks impressive when it starts with a big number, but actually doesn't necessarily mean very much because by the time it's got to a residual value, it's no longer working. So this only takes that time to reach a residual. Here's a standard OIT. It drops a lot further and reaches residual at that time. So the antioxidant depletion is being controlled here, as it often is, by the standard OIT. Remember I told you stress crack resistance is a fiction. The value that you get on the manufacturer's sheet and that you get when you test it straight off the roll is only in part a material property. A lot of it's due to stresses built up in manufacturing. If you let those stresses relax, you go to the true value, SCRM. And that takes time. But that's what's going to control stress cracking in the field. So what we need to know is what is SCRM, and what we need to know is what are those antioxidants doing in contact with our fluid that we're trying to contain. Now, once they've depleted, there's an induction period, and then the polymer starts to break down. And that's when we drop from SCRM down to failed. I do want to point out to you that the drop from SCR naught to SCRM is not degradation. There's nothing wrong with the geomembrane. All that's happening is those residual stresses from manufacturing have relaxed. Now, this can be an important issue in the field because you buy some rolls for your project and you've still got a couple of rolls left over. So you want to keep them next time you want to put down some geomembrane. And your consultant comes along and says, oh, well, we better check it. We'll check its stress track resistance. And they do it and they say, oh, it's dropped by 30%. We can't use that. Well, did it really drop by 30%? Or have you simply allowed that stress to relax? The only way to know is to do a test to get SCRM and say, okay, am I above it or below it? If I'm below it, it's degraded. If I'm above it, you've just relaxed some stresses. You can still use the roll. Once it drops to a nominal value, typically 50% of its true value or the specified value, we say it's reached nominal failure. Now, does that mean it has failed? No. Because to fail, we need two things to happen. We need a drop in resistance, and we need the resistance to be less than the stress is trying to sustain. If we are geotechnical engineers, we're used to saying, okay, I've got a factor of safety. What's a factor of safety? It's a ratio of the overturning moments to the restoring moments. So if I am going to look at what is the strength versus what is trying to cause failure, it's when they come one that we say we've got a factor of safety 1. And so if the strength drops to less than what is the overturning moment, then we have failure. The same thing with stress crack resistance. If I've got 3% strain, I will fail a lot later than if I've got 6% strain. If I've got 10% strain, I'll fail even earlier. And so service life is not just a function of material, it's a function of the stress the material's been subjected to, which is design. And if you have a poor weld in an exposed geomembrane in a cold climate, you could have stress cracking within a month, a year, 2 years of installation. Why? Not because the material is aged, but you place that when the temperature was, say, 5 degrees, and your temperature's just dropped to -40. What happens? Material contracts. And if it's locked in at the edges, goes into tension. And that tension, if it exceeds the resistance of the material, it will fail. And where is the resistance weakest? Usually at the wells. So stress cracking can occur. And it's not just in cold climates. Same thing happens in Australia. When they weld it at 45 degrees C, and the temperature drops to 10 degrees C, that's all it takes. It cracks. So you've got to think about the environment in which it's going to be used and account for that in the design. Stress cracking here is due to wave action, fatigue. Stress cracking here is due to poor welding. With experience, you can look at that weld and see too much heat and pressure. And over time, on a cold day, it failed. So how can current knowledge of geomembrane performance be used in selecting a geomembrane for a specific project? We've got to recognize that even from the same manufacturer, we will get different products. Their generic product, their cheapest product, is not the same as their high-performance product. And they may have several high-performance products for different applications. What's important to you is how they react with your particular solution. Now, to really know, you'd like to test it for a decade or more. I'm about the only person who has the patience to do that. So is there a way that we can get a good idea earlier? And the answer is yes, especially with data around that has been tested for decades. So what is a framework for selecting a geomembrane in a reasonable time period? Well, you need to get a group of candidates. And you need some confidence that it will perform. And for example, one of the projects we're going to talk about was for 550 years for low-level nuclear waste facilities. And it's got to have the durability to resist site-specific exposure conditions. So we establish the nature of the material above and below the geomembrane, the chemistry of the mining fluid to be contained, the likely operating temperature, and the desired service life. With that information, you can go to a supplier and ask them, this is what my needs are. What do you recommend? They know to some extent their material characteristics. And they will recommend one or two products as being the best candidates. You can't trust any one of them to be necessarily the best answer. So usually at least two is desirable. 3 is better. And once you advise them and you've got their choice, you then select a group for testing. I've just finished a project for a mining company where they had us test 25 different geomembranes from 5 manufacturers to select one for a tailings storage facility. Now, what do we need to know about the fluid? Well, pH is important. So is total dissolved solids. But what people often forget about, mining engineers focus on the inorganics, and they are important. But the biggest challenge I find is getting to the chemical engineers involved and finding what they're adding to it to process it. Because they're often adding surfactants or foaming or anti-foaming agents, flocculants, and those can be just as important as the inorganic chemistry in the reaction with your geomembrane. Any trace metals, any health and safety issues. I also want to note, and I mentioned this before, that potable water is generally pretty benign, but reverse osmosis water and highly chlorinated water are very aggressive to geomembranes. So let's take some candidate geomembranes for a long service life. And you can see there the initial OIT values range from 165 to 285. This is the HPOIT, ranged from 800 to 1920. No, 700 to 1920. The resins, this is the initial stress crack resistance, range from 350 to 1630. Well, let's drop that one off. It's too low for stress crack resistance. Are they all satisfactory for a design life of 550 years, 1,000 years? Which is the best? Well, the index properties don't really help us very much in answering that question. So what do? We take samples of the candidate geomembranes and we immerse them in a solution that is simulating, or in fact the actual solution that's being contained at different temperatures. And we usually do it in a reference solution. And that allows us to assess performance in a reference solution, and we also have a reference geomembrane. So here they are, they're put in jars, they're put in ovens, and we look at how they change with time. So we test for the OIT, and here's some data for one particular geomembrane in 3 different solutions. And you see the depletion of the antioxidants on the left-hand axis versus incubation duration. And you can see the solution makes a huge difference. The L7 is at a neutral pH. The L9 is pH 9. L3 is not at pH 3. It happens to be a reference leachate. But you can see that the solutions give very different response. Now, that was in the first 100 days. Let's plot it out further. And you'll notice that most of it's gone by that time, but still there's things left. And it turns out they're the important ones. They're the ones that provide the long-term performance. Here is a different temperature and 5 geomembranes in the one solution. They all start at different points, initial values, but you can see that some perform much better than others. Blue started second best and is not doing too well. White started best and is doing pretty well. Green started in the middle of the pack and is doing second best. You can't predict what's going to happen without doing some testing. Now let's look at stress crack. Here's one product. Its initial value is 5,200. Its real value is 2,000. 38% of what that initial value was. Another one, 1,300, real value 600, 50%. Next one's 30%, 60%, 41%, 50%. So the real value is what's going to actually control the performance. MYA here has got the best resin. And then there's LLDPE. And it has 19,000 hours to start with, but 13,000 of those aren't real. 6,000 are. So we get that by aging at 55 to 65 for about 3 months, and we get that change. We also monitor the antioxidants, and we can use the data to predict performance into the future. I won't go into how we do it. Have to accept for the moment that we can. So let's look at some numbers. If I test for project from my testing for 12 months, I project 20 years at 30 degrees C. If I test for 10 years, that increases to 390. The longer I test, the longer the time becomes, because in early times it's dominated by the things that deplete quickly. This is a different product. You can see it's very much the same, and so we can extrapolate it the same. So you can eliminate some unsuitable geomembranes, but you cannot select the best based on initial properties. You need to test a number of candidates for your exposure conditions, or you need to select ones that have already been tested for very similar conditions. But you need to be sure the conditions are similar. 3 to 12 months of testing helps select the most compatible product. But predictions on this will be very conservative. They'll be erring on the safe side. And you need to use comparators to obtain better predictions. The moral of this story is if you want to select a good geomembrane, start early. People want to leave selecting the geomembrane until they're about to install it. Big mistake. You need to start early, select it well before you're going to need to install it if you want good long-term performance. So the predictions I've just given you are based on stage 1 only. They're aggressive. They don't represent the true service life. They are very conservative. Now, aged in a jar is not the same as in a liner system. And by doing tests both ways, in a liner system subjected to leachate or tailings, subjected to stress, subjected to temperature, we can compare the performance of the same geomembrane with that in a jar. And that allows us to correlate performance and get a relationship, which is temperature dependent. So with a geotextile protection, there's a factor of about 3. With a sand protection layer, it's up to around 4. So protection layer makes a difference to how long the antioxidants are going to last, not just the stresses, but the antioxidants. So good protection layer extends the life of your geomembrane from both minimizing stress and minimizing the loss of antioxidants. So to estimate service life, you need to consider the candidates. You consider the time to nominal failure by beginning with the time to depletion of the antioxidants. And then from comparatives, you can estimate stages 2 and 3. Just finish off with showing you an example or two, crossing the range that we deal with in mining applications. MXC15 we've been testing for well over a decade now, and you can see that the projected times in the field vary depending on the mining solution. They're longest in water, and worst at pH 13.5. MXTB20 is from the same manufacturer with a better antioxidant package and thicker. Under the same conditions, you can see 480 years compared to 3,500. Now, do we believe 3,500? It's a projection a long time out. There are error bars associated with that get bigger the further out you get. But the point is it's a long time, and it's a lot longer than 320. So having an appropriate geomembrane or GCL is a necessary condition for good long-term performance. However, it's not sufficient. A good design is essential to minimize long-term strains, keep them below 3%. And this must be combined with good construction to avoid introducing long-term strains in the construction process. And finally, the designer must have considered the exposure conditions between installation and final performance and have taken appropriate measures to ensure good long-term performance. And this shows you some of the things that induce stress. Water pressures where you've got differential settlement. Down drag when you've got tailings or anything that's going to consolidate. Water pressures can build up underneath the geomembrane in some cases. Differential settlement with loading on top. Melting ice below it. Stiff protrusions in the subgrade. Ruts and stones. Particularly isolated stones in a subgrade. And trampolining, which I mentioned earlier. It's the counter to wrinkles. If the geomembrane is at a temperature higher than when it was locked in place, it'll get wrinkles. If the temperature of the geomembrane is lower, it will start to go into tension. And anywhere you have a change in grade, it will lift up. And if you were to cover this now, you're inducing huge tension in addition to what was originally there by the pressures that are trying to push this back to the surface. So we need to be careful not to lock in too many wrinkles and definitely not to lock in tension. So I've dealt with an approach that one can adopt, and I think I will conclude at that point.